So in this video, I want to talk about different ways of thinking about functions of several variables. And this is important for understanding the intuition behind certain results that involve the gradient, for instance. So in multivariable calculus, you have functions of two independent variables. So you have f of x comma y, and then that's often using a third variable z. And then you have functions of three independent variables, x, y, and z. And then there's usually a fourth variable for the output, which is called w. So for the first case, you can have something like f of xy equals x squared y plus e to the xy or something. And then, plus x minus y plus 7. And another example, well, for a function of three variables, you could have f of xyz equals xz plus 3x squared minus y plus the natural log of y squared z, or something like that, right? So just three independent variables. So there are a couple ways of thinking about these functions. And lots of people and books, when they're explaining multivariable calculus, will use one of these analogies to help explain the results that they're talking about. So there are a few ways of thinking about these functions, especially for functions of two independent variables. So let's look at functions of two variables. So this first case would be a function of two variables. When they say that, they mean two independent variables, x and y, right? This w would be a function of three variables because there's three independent variables, x, y, and z. So let's go back to thinking about how to think about a function of two independent variables. Z equals f of x, y. So there are two kind of main ways of thinking about a function like this. And that is the mountain point of view and the temperature point of view. That's the names I have given them. So what's the mountain point of view? The mountain point of view is you have your x comma y and your z, and you have these axes. So here's your x-axis, here's the y-axis, here's the positive z-axis, and of course it just goes back like this. And then you look at the graph of the function. So you take your f of x comma y, so you plug in your x comma y here. So it's on the xy plane, and then you get the output x comma y comma f of xy. And that has three components, and then you get this point, and then when you graph all the points, you get like a surface. So you get some surface like this. I don't know, some kind of surface, like maybe like this, and your point x comma y is on the xy plane, and then you have this surface that's kind of sticking out. So this is when you graph all the x comma y comma f of xy. When you graph all these triples, you get a bunch of points in three-dimensional space, and then that would be this kind of surface. So you could have so for example, you could have something like f of xy equals x squared plus y squared. And if you graphed that, you would get this paraboloid like this. So that's what I call the mountain point of view. You're looking at the graph of the function, and it has a certain shape. Like it could be a sphere. It could be a well, it wouldn't be a sphere if it's the graph of a function, but it could be a bowl kind of thing. It could be just any sort of surface. That's the graph of a function. Okay, so that's the mountain point of view. And then there's another way of thinking about this, which is the temperature point of view. So what's the temperature point of view? This point of view, you're not graphing the function. You are looking at just the xy plane. So let's look at f of x comma y equals x squared plus y squared. And what this is saying is, think about the function as the temperature at the point x comma y. So for example, let's say that you are a bug on this surface, on the xy plane, okay? And you could be at one of various points, and the temperature of the point that you're at is given by this function f of xy. So for instance, if you're at 0, 0 at the origin, the temperature is 0 squared plus 0 squared, which is 0. So at the origin, it's 0 degrees. Okay. What happens if you're at the point, 1, 2? Well, if you're at 1, 2, then the temperature is 1 squared plus 2 squared, which is 5. Okay, so 5 degrees at the point 1, 2. And so here, you're actually thinking about your function not in terms of a picture, right? Like you're not actually, in this point of view, you're not actually graphing the function. You're just thinking about like each point on your, on your domain has an output, which is a temperature. Like each point has a temperature, and you're not necessarily graphing the temperature. So for instance, this is helpful when you're thinking about level curves. So if you're thinking about like the level curve, for example, let's say you had the level curve z equals 9, right? The level curve is when z equals 9. That's when x squared plus y squared is 9. Well, that would be the circle of radius 3. So that circle of radius 3 is the level curve. X squared plus y squared is 9. That's all the points where the temperature is 9. So at all these points on the circle, the temperature is 9. So we're not actually, graphing the paraboloid. We're thinking about this function as just assigning a number to each point. In this case, you're assigning the temperature to each point. So this point of view, so the mountain and temperature points of view are helpful when you have a function of 2 independent variables. Okay. However, when you have a function of 3 independent variables, the mountain point of view is not good. Okay, so the mountain point of view is not good. How come? Because when you have like where would your mountain be? Because your domain in the mountain point of view, your xy that you plug into the function was on the xy plane, right? Like your domain is this xy plane. But here, if you have a function of 3 variables, your domain is all of R3. So there's no axis to plot the result. Like if you wanted to use the mountain point of view, you would need x, y, z, and then the output, f of x, y, z. Well, this would be 4 components. And you don't have 4 components, right? You don't have an R4 to draw. So because of that, the mountain point of view is not good. What we should use instead, what still works, is the temperature point of view. So what you're doing is you'll have your point. So let's say that your function is, I don't know, x plus y plus z. Just something simple. So then your domain is all of R3, but it still makes sense to attach the temperature at each point. Like it makes sense to say, okay, at this point you have a certain temperature, at this other point you have another temperature, at this other point you have another temperature. And then you have the level surface, which is when the temperature is a given temperature. So for instance, if you have x plus y plus z equals, 68, so if you're using Fahrenheit, or whatever, it doesn't actually matter. The point is that x plus y plus z equals 68, that's going to be some plane. Okay, it's a plane, and all the points on this plane is where the temperature is 68. So the temperature is 68 on this plane. Right? So it still makes sense to talk about level surfaces, level sets, level surfaces for a function of 3 independent variables, and you have a picture of the level surfaces. But you don't have a picture of the graph of this function. So you wouldn't graph f of x, y, z equals x plus y plus z. But you can still get some intuition for what's going on by using this temperature point of view. Of course, it doesn't have to be just temperature, but temperature is a good way of thinking about it. Okay. Then the other thing I want to talk about is the gradient. So where does the gradient fit into these points of view? So this is really important because I think the gradient is confusing, partly because of where the gradient is supposed to be. So let me explain how the gradient is often explained in multivariable calculus and why it was confusing to me when I learned it, and also why I think it's just confusing to a lot of people. So we've seen that the gradient of a function points in the direction of steepest ascent or steepest increase. So what a lot of people say when they're explaining this is, okay, let's go back to this paraboloid example. So let's say that you have the function f of xy equals x squared plus y squared. Okay? So the graph is this paraboloid. You just take a parabola and then rotate it. And you get this bowl shape. So what a lot of people will explain, so let's calculate the gradient. So the gradient of f is 2x comma 2y. This is a function, again, of 2 independent variables, but the output is a vector. Now notice that the vector is in R2, right? For each xy, okay, the vector 2x, 2y is a vector in R2 because it has 2 components. So what a lot of people will say when they're explaining this in a class is they'll say, okay, when they're explaining the steepest descent is they'll say this. They'll say, okay, pretend that this bowl is like a mountain. And pretend that you are a point on the mountain. Like you're on the mountain and you're trying to decide, you want to go up as quickly as possible. And the question is, which direction should you go? And then they'll explain that it's the direction of the gradient. And then they'll calculate the gradient. So let's say that you're at the point 1, 2, well, when x is 1 and y is 2, z is equal to 5, right? So you're at the point 1, 2, 5, and you want to know what's the direction of steepest ascent. Well, the direction is in the direction of the gradient, so that's going to be the gradient at 1, 2, that's 2 times 1, 2 times 2, that's 2, 4. So you move in the direction of 2, 4. Okay, so your unit vector would just be normalized. So you divide by the length, and the length is the square root of 20. So it would be u equals, when you simplify it, it's 1 over root 5, 2 over root 5. Okay. Okay, but where is the 1 over root 5, 2 over root 5? Now, I used to think that since you're going up the mountain, that somehow, if you're here and you're ascending, this way, then your gradient should be like this. Okay, this is not where the gradient vector is. It doesn't point up the mountain. It does not point up the mountain in terms of the mountain point of view. Okay. Where it is when you pretend that this mountain is like clear, like it's a clear mountain. And so you're on the mountain and you can look down, like you can look all the way down on the xy plane. And you see the point 1, 2, technically it's 1, 2, 0, directly below you. So 1, 2. Then it's on this R2 here. So this, you're thinking of it as R2. Okay, you're thinking of it as with two components. So then your gradient is 1 over root 5, 2 over root 5. That would be, so this is the x-axis, that's the y-axis. 1 over root 5, 2 over root 5 is like this way. This way. So that's, in terms of this mountain point of view, that's where the gradient is. So that's what they mean when it says that in terms of the mountain point of view, that the gradient is pointing in the direction of steepest descent. It's like if you pretend that you are on a clear mountain and you're looking down and you see this flat plane and then you see the vector, which has two components, that is pointing in the direction of steepest descent. So where would you go? You would go, so you take this vector, u, and then you look at like the cross section with this vector, and then so here's the point, and then I'm just going to draw a different kind of perspective of this. So here's the point, and then when you go down, you're at this point 1, 2, and you have this vector, which is u, and then you take a slice along this plane. So you take let's see here. So you're on this paraboloid. Make this a better picture. If you slice it, see, if you imagine taking this vector and then taking a plane that's parallel to this vector and then slicing the paraboloid, you're going to get this cross section, and it's going to look like that. Does that sort of look like that? And then you would go in that direction. So you would move this way. So you take this cross section of the paraboloid with this plane. So yeah, so that's the explanation of where the gradient is. It's not actually pointing in the direction. Like if you imagine like that your graph of the function looks like this, say, and you are here. The gradient and the top of the mountain is like here. You know, you're not actually, it's not pointing to the top of the mountain. It's not pointing perpendicular or parallel or anything like this. That's not where the gradient is. It's in R2. Okay. So that's where the gradient is if you use the mountain point of view. And the temperature point of view, it actually makes, I don't want to say more sense, but it makes sense. So in the temperature point of view, let's go back to the temperature point of view. So you have your function f of xy, which is x squared plus y squared, and you're at the point a comma b, which is 1, 2. So in this case, when you think about the function in the temperature point of view, you have the point 1, comma 2, so you're here, let's say this is 1, comma 2, okay? And each point has a temperature. Well, let's look at where the temperature is equal to a certain constant for various constants. So right now, the temperature is 5, right? We know that the points where the temperature is 5 is a circle centered at the origin. And that's not a very good circle centered at the origin, but right now, your temperature is 1 squared plus 2 squared, which is 5. So we're thinking of f of xy as the temperature at xy. And you want to move in a certain direction that will make the temperature go up the fastest. That will make your rate of change of temperature the fastest, the largest rate of change. And the various level curves of this function are circles. So, okay, maybe this is where the temperature is, 9. Okay, maybe, okay, this circle is where the temperature is 10 or something, and then at the origin, the temperature is 0. Right? So as you go out, in this particular example, since your temperature is x squared plus y squared, as you go out, you get hotter and hotter, and the lowest temperature is 0. And what this is saying is that if you had to go 1 unit to maximize the rate at which the temperature increases, it would be in the direction 1, 2. Right? So we found that the gradient at 1, 2 was equal to 1 over root 5, 2 over root 5. So here, since you're thinking of yourself as like a bug or a particle on the xy plane, when you're moving in the direction of the gradient, you're actually moving on the plane. So this way of thinking about the gradient makes a bit more sense in terms of the temperature point of view, as opposed to the mountain point of view, where the way that you're going up the mountain isn't actually where the gradient is pointing in. Okay. So hopefully that if you're confused about where the gradient is, that this point of view clarifies things a bit more. And when you're looking at functions of 3 variables, w equals f of x, y, z, then the gradient does make more sense. So now you think of like a bug that's flying. So this is your temperature at x, y, z. So pretend that it's x squared plus y squared minus z squared or something. And you're at the point 1, 1, 1. So let's say that, say this point is 1, 1, 1, and you're a bug, and right now the temperature is 1 squared. So the temperature at 1, 1, 1 is 1 squared plus 1 squared minus 1 squared. That's equal to 1. So you're currently 1 degree, and you want to know which way do you fly, right, to maximize how quickly your temperature is changing, to maximize the instantaneous rate of change of temperature. Well, you take the gradient, and it's 2x, 2y minus 2z. You evaluate it at where you are, so it's 1, 1, 1, and then you get 2, 2, negative 2. So, and then to normalize this, to get a unit vector, you just divide by the length. Well, the length of this is the square root of 8, so you're going to get 1 over root 2, 1 over root 2, negative 1 over root 2. Is that right? I think so. Is that normalized? Let's see. No, it's not normalized. What is the magnitude? Okay, I'll do out the computation. So the magnitude, square root of 2 squared plus 2 squared plus negative 2 squared. Okay, it's the square root of 12. So this is 2 root 3. So it's actually 1 over root 3, 1 over root 3, negative 1 over root 3. Which is down, right? So it's like this. So this would be the direction that you would fly in to make the rate of change, the instantaneous rate of change of temperature as large as possible. So this case, the gradient really is like, in R3. And in the temperature point of view, you're thinking of where you are as being a point in R2, and then the vector is in R2. The gradient vector is in R2. And then, what's complicated about the mountain point of view is that your function is a function of 2 independent variables, right? But then in the mountain point of view, you're thinking of yourself as a point in R3. And that's why it's confusing. Another reason why it's confusing is that sometimes the gradient really is a vector in R3. So don't mix up, like let's say you're taking a multivariable calculus class and your instructor, your professor is explaining gradient. Don't mix up the scenario where you're a function of 2 independent variables like this with the case of a function of 3 independent variables like this. Okay, these are like different scenarios. So you have functions of, just to recap, you have functions of 2 independent variables. This is a different scenario than functions of 3 independent variables. And usually for explaining multivariable calculus, for functions of 2 variables, there's the mountain point of view, where you think about the graph of the function, and the temperature point of view. And oftentimes, even though this stuff about the gradient is explained in terms of the mountain point of view, it actually often makes more sense to think about it in terms of the temperature point of view. And the temperature point of view also has the benefit that it also makes sense when you have a function of 3 independent variables. Whereas the mountain point of view doesn't make sense. Okay, hopefully this clarifies any confusion that you may have about the gradient. I think it's something that's pretty confusing because there's lots of different contexts and different examples. Like some books will start with a function with 2 independent variables and they'll switch to a function of 3 independent variables. Okay, thanks.